This presentation speaks to how Transphorm took a well-known, decades-old Cascode solution that was once used in switch-mode power supplies to increase efficiency and applied it to its GaN technology. The result is a practical configuration for a high-performance, highly reliable GaN power solution. The two transistors of a Cascode constitute an ideal transistor. First, it combines the low gate-to-source and gate-to-drain capacitance of the fast-switching ground-source low-voltage MOSFET with its high-voltage silicon MOSFET industry-standard threshold voltage, able to be driven by standard CMOS drivers. Second, it also uses a gate-grounded mishemped GaN JFET stage, operating in its native depletion mode at its highest electron mobility, which doesn't present the gate oxide or reliability challenges sometimes experienced with wide bandgap enhancement mode devices. Transphorm is one of the few, as well as the only, pure-play GaN supplier that is vertically integrated. It owns the GaN FET design and the epi starting material and wafer processes. Owning this value chain gives Transphorm the flexibility of a multi-dimensional adjustment scheme in order to offer its customers the best-in-class reliability and performance in the market. Adding to this advantage is its dream patent portfolio, as labeled by NoMade, a patent and technology market intelligence organization. Transphorm offers the largest patent portfolio in the market, encompassing many areas from design, materials, processes and packaging, through to applications. Transphorm took the practical Cascode circuit structure and evolved it over time using its GaN FET technology. Its first-generation platform was released in 2014 and was generally described as a multi-chip module, as it included a low-voltage silicon MOSFET, a GaN JFET, gold wires, a chip resistor, and an aluminum nitride shim. Although it operated well and offered best-in-class robustness and reliability for a time, its costs were high. Transphorm has since released 3 generations, with the most recent being Gen 4, now branded as Super GaN. Today, Super GaN is Transphorm's highest performing, simplest to package, lowest cost GaN platform. It still delivers the market's best-in-class gate robustness and reliability, a design focus that has led Transphorm to offer the industry's first JDAC qualified as well as the first automotive qualified GaN FETs. Looking left to right, one can see that Transphorm has moved from a multi-chip module to a simplified-looking single MOSFET solution, where there are now only 2 chips. A low-voltage MOSFET bonded over active on top of a GaN JFET with aluminum bond wires on the gate, drain, and source. Note that this solution offers even fewer bond wires than the market's current silicon carbide Cascode solution. With the simplicity of packaging comes the simplicity of both designability and drivability. Offering a silicon superjunction-like threshold voltage allows standard off-the-shelf gate drivers or controllers with integrated gate drivers to be used. There is no need for device gate drive protection, resulting in a limited amount of external passive components required to maximize its performance and density. Being that the high-side GaN device's snubber resides on the non-switching DC link voltage node, efficiency is not affected. So, at a minimum, only a switch node snubber may be required on the low-side GaN FET, though our latest Super GaN devices don't require one at all. Many customers using silicon superjunction MOSFETs, silicon carbide MOSFETs, and even enhancement mode GaN devices today are using Kelvin source package connections. This is a low inductance path from the source of the device back to the ground connection of the gate drive shown on the far right circuit. In those MOSFETs, these Kelvin source connections are used to reduce source inductance, resulting in a faster switching device. Whereas enhancement mode GaN FETs require a Kelvin source to protect the sensitivity of the device's gate. Transphorm's GaN FETs do not require a Kelvin source at all. This is because they operate as a voltage-controlled device, just like silicon and silicon carbide MOSFETs, with both high threshold and absolute maximum gate voltage levels. Transphorm uses a GaN highly electron mobile transistor that offers an electron mobility of approximately 1.5 times that of silicon and more than 2 times that of silicon carbide. This results in much faster switching transitions regardless of having a Kelvin source, which may be validated on the next slide. Admittedly, Transphorm's original surface mount packages used Kelvin source connections. But as they evolved, the applications determined what was most appropriate for the technology. Case in point, you can see the switching waveforms of two surface mount devices, one on the left with a Kelvin source connection and one on the right without a Kelvin source connection. The one on the right shows lower overshoot and oscillations during turnoff, which helps reduce the stress on the device, as well as the EMI emissions testing. Getting back to the difference between Transphorm's voltage-controlled GaN FETs and the current-controlled enhancement mode PGaN devices. The enhancement mode device has 1 volt or so of headroom on the gate when the channel is fully enhanced or turned on. So, damage can happen quite easily if not protected. If a Kelvin source is not used, then any large current transient on the source could cause ground bounce at the gate drive, which may in turn cause the device to exceed its absolute maximum gate rating and damage the device. This ultimately causes a real concern about long-term reliability. To combat this, additional passive devices are used to protect the gate. However, this solution takes up additional room, adds additional cost, and affects the power stage's density. As Transphorm has evolved its GaN technology, costs have decreased while performance has increased. Shown here is our latest Gen 4 35 milliohm device compared to a comparable market-available silicon carbide device tested in a synchronous boost converter operating at 100 kHz. The result shows an increase in performance of up to 20% from 3 kilowatts through 7.2 kilowatts. The adoption of GaN has not only come from Transphorm's GaN devices, but also from joining forces with Tier 1 semiconductor suppliers such as Microchip, a well-known brand. Many power electronic engineers use Microchip's microcontrollers and firmware development environment. Transphorm's expertise resides in the GaN domain, whereas Microchip's resides in the firmware and worldwide support of it. Bring the two together, and we're enabling our customers with a strong starting solution for the bridgeless totem pole power factor correction topology. This gives engineers an opportunity to better understand GaN technology while reducing time to market. The digital bridgeless totem pole partnership with Microchip was formed in response to an educational need for Tier 2, Tier 3, and Tier 4 power supply design houses. Alternatively, should engineers want to stay with an analog-type design, we also now offer an analog totem pole solution, again enabling engineers to A. become familiar with our GaN FETs, and B. use as a starting platform to reduce time to market. Regardless of whether the digital or analog solution is used, a greater than 99% efficiency can be achieved. So now, we've addressed how Transphorm has evolved its GaN FET technology and supporting design tools to increase high-voltage GaN awareness and adoption. One of the remaining and more important areas that Transphorm is asked about is high-volume reproducibility. Since Transphorm owns its epi and manufacturing processes, high-volume, high-yielding wafers are produced. High-volume reproducibility is critical to the success of any new or existing technology. As shown here, through a joint venture with Fujitsu's AFSW fab located in Aizu, Japan, Transphorm has high-volume capability and silicon-like defect densities starting as early as 2015. In summary, Transphorm's practical approach to GaN platform and device innovation, along with its practical approach to enabling partnerships and design tools, is yielding the results necessary to drive the market to mass adoption, all while maintaining the high-voltage GaN industry's highest reliability and performance.